Hey guys, welcome to another lecture. In this lecture, we're going to focus on ways of finding the global maximum or minimum to a function. So if we're trying to maximize this function right here, we can see that it has two peaks. And if we follow a basic heuristic method, basically go the direction where you're increasing, that could work in certain scenarios. So say we start out here on the left-hand side. Well, we can simply look around the neighborhood of where we're looking at. So we look a little to the left, we look a little to the right, and see, well, in which direction am I increasing? In this scenario, you'd be increasing if you head towards the right. You'd be decreasing if you head towards the left. You don't want to be decreasing, so you head towards the right. And you continue heading towards the right until you eventually land to this global maximum. That works great in the situation that you get a good starting value. But say you're absolutely blind to where a good starting value might be, and you just happen to land here on the left towards the tail end of the function. Sorry, on the right hand side of the function. Well, in this scenario, you would look towards the left and you look towards the right. Well, if you move towards the left, you increase. So you'd continue doing that and keep going until you stop. And because you might not know what the function really looks like, you might just assume that, hey, I reached the global maximum. But in fact, you didn't. You're stuck at a local maximum. So in this lecture, we're going to focus on ways of escaping that local maximum and ways of exploring the search space of this function in order to eventually find the global maximum. So the algorithm that we're going to be exploring is called simulated annealing. In this algorithm, we basically have a probabilistic way of moving around the search space, either towards the left, towards the right, up or down, based on some probability. And simulated annealing gets its name. It's inspired by the process of annealing in metallurgy, basically heating and cooling matter. And so think about it this way: the hotter matter is, the faster its molecules move, and the cooler it gets, the slower the molecules move, and the more difficult it is to move around. But before we get into the simulated annealing here, I just want to reiterate what the basic hill climbing algorithm is, the algorithm that I first illustrated when we were talking about that hill climbing algorithm. So in a hill climbing situation where we basically start out at some random starting value, and for some set of iterations, we look around the neighborhood from where we're currently standing at, and we basically choose to move towards the area of the neighborhood where we're increasing if we're trying to find the global maximum. And we continue doing that until we reach some stopping value, or we just converge or basically get stuck at a local maximum, or by some luck get to the global maximum. Simulated annealing varies a little bit. So again, it's a probabilistic approach. It's stochastic, so we have some randomness in how we're moving around in the search space of this function that we're trying to maximize. So we start out by finding our function that we're trying to maximize. We call that h. We get some starting solution, some candidate solution, x, and then we set some temperature. This can be 1, 10, 100, something or greater than 0. And again, for some set of iterations, we're gonna sample from a symmetrical distribution, and this is just like a small value from, say, a uniform distribution or a normal distribution, something easy. We're going to add that little fuzzing, that little noise that we sampled to our current position, and that's going to be our candidate solution that we're going to potentially move towards to. We calculate our probability value by getting the difference of where we're currently at and using our temperature. Now, if our temperature is, say, 100, well, the probability that we're going to accept the candidate solution is going to be high. If the temperature is low, the probability is going to be lower. Then once we calculate our probability, we either accept or reject, again, based on that randomness, and we update our temperature. And there are different ways of updating our temperature. I'll talk a little bit about that right here, actually. So again, as I mentioned earlier, the greater the temperature is, the greater the likelihood you are to move around the function. And this helps you basically escape local maximums. So instead of just getting stuck, you have a chance to jump to the complete end of the function and really get a feel of where the global maximum might be. And as t gets closer and closer to 0, well, now you're start behaving a little more towards more like a greedy hill climbing algorithm, where you really only move if that increases the function that you're trying to maximize. And a good starting value for t might usually be like 1, 10, or 100. You kind of have to play around with different t values and see what benefits your specific function. And there are different suggested ways of setting t and updating t. One way is by using this function, where I is just the iteration that you're currently at, either the first, the second, or third, etc. And if you follow this link, you can follow a reference and read up on different ways of updating temperature and setting temperature. And these are just the two references I used for this lecture. So right now I'm using an IPython notebook. And so in order to follow through this next example, I'm going to need to import the NumPy library, which is the math library, matplotlib for plotting. In the cell, I'm just defining my h function. That's the function that I'm trying to maximize. And this is what it looks like. So it's lumpy, it's noisy, and if you're trying to use a greedy hill climbing algorithm, just by the lumpiness, there's plenty of opportunities to get stuck at a local maximum, some of which just aren't even close to global maximum. So here's the the simple greedy hill climbing search algorithm. And just as I explained above, we start out with some random starting value. Here I set it to 0 automatically, but you can set it to anything. And for some number of iterations, we're going to add some noise. That's this variable u. So we look to the left and we look to the right, and based on which value is greater, if moving towards the left is greater, we accept the left candidate. Otherwise, we accept the right candidate. And we do this a number of times until we reach convergence. And so here I have an example where I try to use the hill climbing algorithm to try to find the global maximum. You can see it tried to climb up based on just my random starting value, and then it got stuck. It didn't reach the global maximum. So next, we're going to explore what the simulated annealing algorithm can do. And that's this function here. So we get some random starting value, and then for some set of iterations, we get a proposal. We calculate our probability of accepting that proposal, and then we either accept or reject it based on that probability. And finally, we update our temperature, and then we rinse and repeat. We do this 1,000 times. So here again is that same function. And here I set my T to 4. So that's the temperature. I set it to 4. And here you can see what the performance is of this run. So we started out here at about negative 0.5. And then we jumped over here at, what is that? Something around 0.1. And then we jumped around again here to about 0.75. And eventually we reached this value that gets us pretty close to the global maximum. And the global maximum is about 2. And you can see that we came pretty close to 2. Between 2 and 1.93, the error is pretty negligible, but you can see that there were a couple of opportunities for the algorithm to get stuck, and it didn't. It jumped out of those local maximums, and it headed towards the global maximum. So again, just to summarize what we saw here, we saw that there are stochastic ways, Monte Carlo methods, to finding a global maximum to a function. And if you found this interesting, you can continue on to the next lecture where we're going to continue exploring the simulated annealing algorithm, this time to find solutions to combinatorial problems, which are basically tons of problems in operation research. And so, again, if you found this interesting, just continue on to the next lecture. Thank you.